All right, thanks everybody, SNOMAS organizers, the whole community for inviting this session and putting Martin and me in trouble to organize it. We have been working since, I think it was July to put this, beginning of July to put it together, maybe end of June. And, you know, we invited a number of people that told us go away, but then we had such a big pool of people to organize this session that we think we are going to have a lot of fun and learn a lot about the status of the intersections of quantum with high energy with quantum. So I will go very briefly through the agenda. The introductory talk is by Joe, and he will talk to us about the landscape internationally for quantum and HEP. Then we will go to our earliest career speaker, who just got a prize in 2020, or he finished his PhD rather in 2020, Geoff Pennington, and he will tell us some really beautiful way of quantum and HEP intersections in terms of solving really a very fundamental problem that in the past 10 years has kind of dogged the community, the formal theory community, the non-formal community of HEP and HEP in general. The National Quantum Initiative, we are very privileged to have in person here Paul Dabar, who actually launched that in 2018. And then we have a panel discussion with a very distinguished panel discussion with a number of researchers that are very active in this area. And in the end, we close with former NIST pioneer on quantum, Kel Williams. Now I say former because he's still Carl, but he's retired from NIST, but he still works in quantum areas. And we have some pre-recording video remarks, but he will connect also in case there are questions. And so here is the pictures of our distinguished speakers and panelists. And Martin will say a word about each one of them so we get started without further delay.
So thank you very much, Maria. It's my pleasure to now introduce the participants in this session. So Aaron Chow is a staff scientist at Fermilab. He's head of the Quantum Devices and Sensing Thrust of DOE's Quantum Science Center, and he is PI of a HEP quantized project. Anna Grassolino is a staff scientist at Fermilab. She's director of DOE's Superconducting Quantum Materials and Systems, SQMS, NQI Center, and she's been the recipient of a Presidential Early Career Award. Kel Williams is the president and CEO of CJW Quantum Consulting. He's been division chief at NIST and senior executive and deputy director of the Physical Measurement Laboratory of NIST. He is the co-founder of the NIST Quantum Economic Development Consortium, QEDC. Christian Bauer is a staff scientist at Lawrence Berkeley National Labs, where he's head of the High Energy Physics Theory Group. He's received DOE Outstanding Junior Investigator and Presidential Early Career Awards. Geoff Pennington is a visiting professor at the Institute for Advanced Study and professor of physics at UC Berkeley. Just last year, he received the New Horizons Physics Prize. Joe Licken is Deputy Director for Research at Fermilab, and he is head of Fermilab's Quantum Institute. Krista Zvore is head of the Azure Quantum Research Group at Microsoft. She's a fellow of the AAAS, and in 2018 was listed as one of 39 most powerful female engineers. Maria Sparopoulou, who you've met, is the Shang-Yi Chen Professor of Physics at Caltech, and among her accolades, she's fellow of the AAAS. Monica Schleyer-Smith is Professor of Physics at Stanford University. She's received multiple awards, including a MacArthur Fellowship. Paul DeBar is a distinguished visiting fellow at Columbia University and CEO of BQT. He was DOE Undersecretary for Science between 2017 and 2021. Paul is a graduate of the United States Naval Academy and of Columbia Business School. Ravi Naik is a research scientist at Lawrence Berkeley National Labs. He's head of measurement in the Advanced Quantum Testbed at Berkeley LBNL. Ravi received his PhD in 2018 from the University of Chicago. Xinjie Yu is a research staff scientist at Brookhaven National Laboratory, where he's lead of the artificial intelligence and quantum machine learning research effort at Brookhaven. Travis Humboldt is staff scientist at Oak Ridge National Laboratory. He's director of DOE's Quantum Science Center, the NQI Center led by Oak Ridge National Laboratory. He's also director of the OLCF Quantum Computing User Program. He has many accolades, including a DOE Early Career Award. And finally, myself, I'm Martin Savage. I'm Professor of Physics at the University of Washington and Senior Fellow in the Institute for Nuclear Theory and PI of the Incubator for Quantum Simulation. And with that, I'll pass back to Maria. Thank you.
All right, great. Thank you, Martin. And I would invite John Licken, who gives the first talk, to come to the podium, and let's put the talk. Would you like to use a lapel mic or is the podium mic okay?
I think we'll stick with this one.
Or is it this one? This one's just fine.
That's it, yeah. Work? Yes. All right. So I'm going to give you a quick 15-minute tour through the HEP QST landscape. So let me start with foundations. I think most of you know that the origins of quantum science and technology to a large extent arose from scientists confronting challenges in our field and the related field of trying to understand gravity. And this, of course, goes back to people like Feynman inventing the idea of quantum computing, quantum sensors going back in some sense to Heisenberg, but certainly back to Carlton Caves, who was a student of Kip Thorne, basically invented the idea of quantum sensors, which eventually got used in LIGO, and then quantum communications and entanglement, which goes back to the famous CPR paper, and then also got resurrected in a large form by Hawking with the black hole information problem. So the whole point of that history is that we have had and continue to have the HEP community a large footprint in what I would call the intellectual high ground of quantum science and technology. We should be proud of that. We should be thinking about that here at Snowmass. And it's because it underlies the foundational questions of our science. And you'll get some inspirational modern version of that from Jeff Pennington's talk. Then talking about this landscape, there's sort of two directions you can go, and we often do it in both directions. So let me also do it in both directions. So here's the direction of QST for HEP. So what is the quantum world doing for us? So other communities, as you know, have growing scientific interest in QST and are making important advances. And this includes our friends in condensed matter, material science, AMO. They're have developed superconducting qubits, ion traps, amazing things with cold atoms. Topological materials have become a real thing, spin-based sensors, and the list goes on and on and on. So these are all amazing things which we in HEP should be paying attention to. And then, of course, the whole world of high-performance computing is thinking about what's next, as you'll hear as Moore's law sort of peters out. And this is part of that answer seems to be quantum hardware. And then there's the whole standalone field of quantum information science, which is really quantum physics in the language of information theory, which is really a profound thing that I think most of us have not paid enough attention to. And then quantum metrology, which is pushing the limits of sensing and precision measurements, and have already done many, many amazing things. So we have a lot to gain from collaborating with these communities. And I think we have started to realize that, but we haven't taken enough advantage of it. And I think it'll be a big part of our future going forward. Then the other direction is also equally interesting. So other communities, these same communities I've been talking about, have started to realize or already knew that we in HEP bring value to the quantum ecosystem. And we should also be proud of that and be thinking about what advantage we can take for what we're interested in. So part of that is just the fact that we have lots of hard quantum problems, and as we'll see examples of that as we go along here. Another part of that is because of the demands of our science, we are the world leaders in many technologies because we had to be, because we needed them, that are now relevant to the larger quantum ecosystem. And this includes superconducting RF, advanced control systems, as you see Gustavo Cancelo showing off his board there, fast timing cryogenics, and the design, scale up, and deployment of sensor systems at scales that other people find quite amazing. It's also true that because of the demands of our science, we are early adopters of new technologies because we have to be, and of new approaches. And that makes us interesting to this larger ecosystem because we're not afraid to get our hands dirty with things like NISC-era quantum computers and simulators, hybrid quantum computing systems, and sensor network prototypes. So this is something where we can contribute to the larger ecosystem by saying, yeah, just give me whatever you have and we'll see if we can do something interesting with it. And furthermore, because of the nature of our experiments, as we all know, we have to take the long view. So for example, LHC and Dune will still be operating 20 years from now. So when you say, oh, we're gonna have quantum computers that are really great 20 years from now, that's actually relevant to experiments that we are launching now or have already launched. And we also have experience from things like lattice gauge theory, which took 30 years to mature, but we put a lot of investment in it. And when we finally got it to work, it was incredibly valuable to our field. So we understand that taking the long view is the right way to go, and we have experience doing that. So now let me get back to what's actually happening in our world. So I'm just going to talk about the DOE world of high energy physics. So as you know, in the last SNOMAS P5 process, quantum did not exist as a topic. I don't think we brought it up one single time in the P5 deliberations. And then there was a first order phase transition that occurred in 2018 with the DOE National Quantum Initiative. And we have the architect of that initiative here, Paul DeBar, who will tell us more about it. And this is my little example, this photo of the fact that this was a first order phase transition. So in the summer of 2018, we applied to do a workshop for the following summer at the Aspen Center for Physics on the intersections of HEP and quantum, exactly what we're here today. And the workshop was turned down because it was considered premature to be having a workshop on such a strange topic. So we went ahead and did the workshop anyway the following May using funding from the Kavli Foundation. And then of course, the kind of thing that happened is the kind of thing that happens all the time now, which is you get an expert from NIST and an expert from Fermilab and an expert from NASA JPL, as you see in this photo, together, and they have a conversation and they start a collaboration, which is now doing something amazing that's going on even today. This is 2019. So we went from sort of, this is inconceivable to this is actually happening almost overnight. And of course, the other reason this happened in 2018 was because funding showed up. So the DOE HEP quantum program, which is called Quantize, started funding people in 2018, and there were 41 initial funding awards. And so when you go from essentially no funding to 41 awards, you might imagine that something happens fairly quickly, and that's indeed the case. Furthermore, this HEP program was highly leveraged from the very beginning by explicitly encouraging the kind of collaborations I'm talking about with other scientific communities and other programs and agencies that were also starting to ramp up their support for quantum. And that includes other DOE programs like OSCAR and BES. It includes the Department of Defense, NASA, NIST, nuclear physics and DOE, NSF, et cetera, et cetera. So it was that leveraging, was the fact that the whole world was sort of ramping up quantum that allowed HEP to do this very quickly. Furthermore, experiments started almost immediately. As far as I know, the first actual quantum experiment that was financed by HEP Quantize was dark SRF at Fermilab, which began already in 2018. And by 2019, there were 2 awards for other quantum experiments, which were actually based on atom interferometry, which of course is an expertise that's was totally outside of HEP. Then there was, in some sense, another first order phase transition in FY21, because in August of 2020, we had the establishment of the National Quantum Initiative DOE centers, the 5 centers, and this included the HEP-led SQMS center at Fermilab. And so this, I think, took us to a whole nother level, which is still playing out for HEP's involvement in quantum. So how does this relate to what you're doing here at SNOMAS? So now SNOMAS 2022, quantum is obviously a major activity of HEP. It is not a frontier in the sense of SNOMAS, but instead the way it's organized here is it's integrated into the computational, instrumentation, and theory frontiers, which, as you know, are themselves cross-cutting frontiers, so that's very appropriate. And here you see the conveners of the topical groups that are doing this. But there's quite a bit of activity happening here. My count was 22 white papers with 400 distinct authors, not counting pre-existing collaborations, because, for example, Super CDMS is considering quantum sensors for upgrades. So I'm not counting all the members of Super CDMS. So roughly speaking, this is in HEP is a community of something like 400 people now that are interested in doing a large variety of things. It's also evident from the white papers that this is extremely cross-cutting. It is overlap not only with the 3 frontiers that it's embedded in, but with all of the other frontiers. And I could go through the list here. I think most of them are fairly obvious. Maybe underground facilities is not obvious to you, but in fact, both the SQMS Center and the Quantum Science Center, 2 of the NQI centers, have already underground facilities for qubit testing going on. So underground facilities is also a thing we're doing in quantum. So what's in these white papers? Well, I'm not going to go through all the white papers. There have been talks here at Snowmass, and I encourage you to go, if you didn't attend the talks, to download the slides and see what people are thinking about. But here's just a few highlights. So on this subject of foundations that I talked about before, there's a very nice white paper called Quantum Information in Quantum Field Theory and Quantum Gravity. And here's some of the highlights from that white paper. The first thing they point out is we still don't understand what quantum field theory is at a fundamental level. And so that is a big topic for our field. And recasting quantum field theory in the language of quantum information and entanglement is one way of trying to understand better what quantum field theory is. Another thing we'd like to understand is the quantum origins of space-time. And there we actually have a handle on it. And this comes from the ideas of holographic duality, which predict very specific phenomena, such as teleportation via traversable wormholes that might actually teach us more about how space-time emerges from quantum microphysics. So that's a very specific sort of direction that we can go. Then there's quantum simulation. And here the idea, it's basically the same strategy that Ken Wilson used, which is if you want to learn about quantum field theory, think about how you would explicitly actually simulate it on a classical computer. So by thinking how we would actually formulate some of the problems that we're interested in here on a quantum computer, that process itself of trying to figure out how you would do that is probably going to lead us to insights even before we have the quantum computers to do the simulations on. And then last but not least, there are relations between the things we're interested in and things that the quantum people are interested in, like error correction. And in fact, if you went to Shamik Katru's theory summary, you saw an example of this, which is the connection, possible connection between quantum field theory and quantum error correction at a very deep level. Okay, so another set of white papers is talking about quantum computing. So quantum computers do exist. They are getting better and better. They will at some point become presumably extremely functional. And what are we going to do with those quantum computers? Well, we have lots of hard problems in HEP that are not tractable with classical computing. And just to remind you, real-time strong interaction processes, such as the initial proton-proton collisions at the LHC, are not tractable with classical computing. Neither are the neutrino nucleus collisions that we're going to be doing at Dune, where a neutrino hits an argon nucleus and the argon nucleus does this for a while. That's also not simulatable with classical computing. So that should be enough right there to tell us that we better figure out how to use quantum computing. And if that's not enough for you on the cosmic frontier, non-equilibrium dynamics like cosmic inflation and baryogenesis, if it occurred in the electroweak phase transition, those also we don't know how to simulate very well with classical computing. So we have extremely important problems of our field that are actually the almost poster children for the kind of thing you would like to do with quantum computing if you had sufficient power in that sort of computing. So we don't have those quantum computers today, but just as with lattice gauge theory circa 1980, you can either sit on your hands and say, I'm going to wait until exascale computing comes 30, 40 years from now, or you can actually start figuring out what you can do with the computers that are here today and learn how to do things and learn from gearing up for the computers that we'll have in the future. Also, as you also know in HEP, there are many problems that we do where just incremental improvements can make a big improvement in something that we really care about. You know, if I'm doing $1 billion experiment and I can do something twice as well, that's not an exponential improvement, but it's a big deal for certain kinds of things that we care about. And that includes triggers at the LHC. It includes modeling of hadronization in showers. It includes pattern recognition for things like tracking. Includes anomaly recognition, things we're doing now with AI that could be improved by quantum AI. There's all kinds of applications in our field where getting not an exponential improvement, but a substantial improvement could be a big deal. So what we need to be doing now is looking for near-term quantum advantage for high energy physics, taking into account the fact that we have these imperfect devices, but they're getting better as time progresses. Similarly, with quantum sensors, we have big challenges in our field. It is our job in high energy physics to do direct detection of dark matter if that's possible. And that's very difficult because of the fact that we don't know what dark matter is. So we are trying to do various approaches, but the hard cases we can't ignore, because in the end, we have to try everything until we actually get a success. And in fact, even discovering dark matter in one particular experiment doesn't necessarily mean that there aren't other kinds of dark matter. Some of the white papers point out some of the interesting difficult cases. One is ultralight dark matter, and another is ultra heavy dark matter. And these are both of these are areas where quantum sensors, new kinds of devices that are coming online now, could be developed to handle some of these difficult cases. So there, the idea is that you have this sort of three-step process here, this roadmap for discovery, where you need theorists to explain what are the candidates and signatures that you're looking for. You need a collaboration with outside communities that are the people actually developing these quantum sensors. And then you need some kind of R&D program where you actually deploy examples of these new technologies to see whether you can do a real dark matter experiment with these things. And of course, it's not just dark matter, but I give that because it's the obvious application. And then last but not least, we have quantum networks. So there's a nice white paper about quantum networks. This ties in to a bigger picture here, this quantum internet initiative, which was launched by the then Secretary of Energy, as you see here in the lower right. We in HEP got into this from the very beginning, and this involves things that we care about in HEP, like as soon as you have two quantum sensors, you would like to make a quantum network out of them. It includes also possible applications of networking clocks, and then eventually the idea of quantum telescopes and doing quantum astronomy. So we have interesting applications for this, but at the same time, we are bringing HEP know-how, it turns out, to this sort of technology that is also of unique value. And in fact, we in HEP have built the most performant examples of quantum teleportation networks that anybody has yet done. And here you see the new director of the Office of Science, Dr. Berhe, inspecting our quantum teleportation machinery a couple weeks ago. I also wanted to point out that Cern has a quantum technology initiative, which started relatively recently, but I have the impression that it's ramping up quite quickly. And if you look here at what the initiative includes, this is from the website, you see that it includes all of the different topics that I've just been talking about that are in the US DOE program. So they have a very similar strategy here. This is ramping up fast, and it's working with the larger European quantum ecosystem. And as you know, the European quantum is very advanced, certainly equal to, if not superior to, what we're doing here in the US. So I think this is a very exciting initiative from Cern, and it's something that we in the HEP community should be attaching ourselves to and trying to coordinate with as best we can. And then the last point I wanted to make before I hand it back is the idea of quantum pathfinders. So I already mentioned that the Quantize program supported a few experiments, and this is something we could think about doing, I think, in a more formalized way. So I think this is something for SNOMAS or even P5 to think about. Should we have an actual portfolio of low-cost, high-return Pathfinder quantum experiments? So the reason I say Pathfinder is because I think the idea here is not that you are sort of stepping on the territory of the other frontiers, but rather you are developing Pathfinders using new quantum technologies that then could turn into a cosmic frontier experiment or a precision frontier experiment or a neutrino physics experiment in the future. So I think this is an interesting strategy. It's a strategy that involves small-scale experiments. As you know, small-scale experiments are incredibly good for the health of our field anyway. They provide more opportunities for junior scientists. It's good for attracting a more diverse group of people into our workforce. And it's a good way of convincing our stakeholders that we have things that they ought to be investing in. So you can go read this white paper where we tried to describe a possible way to get to this kind of portfolio and see what you think about it. That's it for me.
I didn't see any questions on the Google Doc or the Zoom. So because we're 15 minutes delayed, what I would like to do, and I was texting with Martin, is I would like to take one question for Joe, and then if he's willing to join the panel, he can take more questions during the discussion. So Joe, I'm asking you first, is that okay? Okay. All right, so let's take one question for Joe and move on to Jeff's presentation.
Could somebody stop the screen sharing so that I can share? It's not letting me while another participant is sharing. Oh, is there something else I need to do?
Yes, go. If you have a question, please go ahead and identify yourself, please. Oh, this was Jeff's to share his screen. Okay, just a second, Jeff. Is there an urgent question? Yes, there was one.
Just a quick question. So for since you mentioned NASA,
one second. We have one in the audience, and then I see Irvine has a question. Go ahead.
Joe, this is Sergey here, right here.
Sergey Nagaitsev from
yes, a quick question for you. Do you see also a need for continuing development of new quantum computing topologies, or SRF? You talked about sensors, I understand, but how about multi-qubit systems that I think we are capable of doing in HEP? Can you comment a little bit on this?
Yeah, I think everybody in the quantum ecosystem would agree that we don't necessarily know that we have the best multi-cubic systems yet, right? And I'm talking here about things that you can scale up. So I think new ideas that are radical in some way are still very much interesting. And if we in high energy physics can contribute to a radical idea, I think that's certainly an appropriate thing for us to be doing.
Irvine yielded for the panel discussion. So Jeff, the stage is yours.
Okay, great. So can people hear me?
Yes,
okay, I'll assume so. Okay, great. So I call this talk High Energy Physics in the Age of Entanglement. In practice, I'm just going to be talking about quantum gravity because that's what I do. But that's not because that's the only physics that I think quantum, these ideas from quantum information, entanglement, and so on are super useful for. I think they're fundamentally a sort of new framework, a new way of thinking about fundamental physics that's going to allow us to tackle old problems in new ways. From sort of black hole information, which is what I'm mainly going to be talking about today, to strongly coupled quantum field theories and all sorts of things that are interest of high energy physics in general. Okay, so suppose I have a book, and for some reason I want to just destroy all the information in this book. Maybe it's top secret, maybe I'm just embarrassed by what I choose to read. But how would I do that? Well, in practice, I might do something like taking the book and shredding it. But the trouble with that is, well, in practice, it's normally good enough. No one's ever going to actually put that shredded material back together. If the NSA cared enough, then they could probably do so. They could fit the little pieces together and reassemble the information. So the information's got less accessible than it was before, but it's still fundamentally
Jeff, could you speak on your keyboard?
Sorry, say that
Could
again?
you go closer to your keyboard?
Yeah, okay. I'll try to. I thought I had my headphones working, but possibly not.
Your mic is your mic comes a little garbled.
Okay.
Information. We can reconstruct it with entanglement.
Yeah, exactly. Okay, so hopefully people can hear. So if I was going to get a bit more serious, then maybe I'd take the book and instead of just shredding it, then I would burn it. And in that case, then it's definitely good enough. No one is ever going to find out the information that was in the book. But in principle, the fact that Schrodinger's equation is unitary means that the information in the book is still there in the positions and the momenta of air molecules, photons, and so on. Okay, so we haven't really destroyed the information, we've just made it completely inaccessible now. So in 1975, Hawking claimed something much more radical would happen if we threw the book into a black hole. Claimed that if you wait long enough, then the information just genuinely vanishes from the universe. That quantum gravity, unlike ordinary quantum mechanics, is not a unitary theory. It's different from every other theory of physics. It's irreversible, and information initially present just disappears over time. So in 2019, there was a load of pretty exciting progress, where for the first time we had direct gravitational calculations that showed that Hawking was wrong, that this information didn't truly vanish. It came back out in the Hawking radiation. And those calculations, viewed in the right light, really come from taking the lessons of quantum information and the ways of thinking from quantum information seriously, and just doing the right calculation to actually see whether the information is gone or not. And when you do that, you get the answer of no, it's not. So I'm going to try and give you guys a sense of how that happened. But firstly, I just wanted to very briefly review how Hawking's argument actually worked. Okay, so let's just start with quantum entanglement. It should be relatively familiar to you guys. But as we all know, quantum mechanics is very, very weird. And one of the ways that it's weird is that you can have a state where the state of the entire quantum system is precisely defined. There's no noise or anything, but the constituent subsystems of that system are inherently uncertain or noisy. So they have to be described by a density matrix that includes classical probability in addition to sort of quantum mechanical states. And these are called entangled states. And of course, the classic one is this Bell state shown here, superposition of two qubits in a 0 state and 2 qubits in a 1 state. So in quantum field theory, anytime you have fields in close to each other in space-time, then those fields always have to be entangled with one another. Okay, this has nothing to do with black holes. It's just a general fact about the universe, about quantum field theory. But in particular, it would be true for fields just inside a black hole horizon and fields just outside a black hole. The interesting part about black hole, of course, is that the black hole dynamics means that the modes just outside can eventually escape off to infinity, whereas the modes that are inside will always remain stuck inside the black hole. So the modes that escape end up being this thermal Hawking radiation, noisy quantum state that is entangled with the black hole. And Hawking produced this beautiful formula shown down here for the temperature of the Hawking radiation. I like to say that, just looking at this formula, you can see how clever Hawking was, how much went into this, because really all the major fields of physics are represented here. So we have, for example, Newton's constant showing up, we have gravity, we have Planck's constant, quantum mechanics, we have relativity showing up, we have thermodynamics, and of course we have circles from the factor of pi. I also want to emphasize for experimentalists in the audience that, of course, for astrophysical black holes, this temperature is vastly colder than the cosmic microwave background. So no actual black holes that we know exist in the universe are actually evaporated. But plausibly primordial small black holes could be doing so. So it's important to note that just because this radiation is noisy doesn't mean there's any information paradox going on here, because this radiation is entangled with the black hole itself, right? It's entangled with the interior of the black hole, and that's a perfectly ordinary thing that happens all the time in quantum mechanics, that things become entangled, and so the individual things are noisy, but the global state of the universe is still noiseless. We still have unitary evolution going on. The trouble with black holes is that this noisy radiation carries away energy. So if we wait long enough, more and more quanta of Hawking radiation will escape the black hole, go off far away. The black hole will get smaller and smaller. And eventually, it seems like the black hole will just completely disappear entirely, and we'll just be left with this noisy Hawking radiation. So at that point, we really would have information lost. And in fact, it's worse than this, because even when the black hole is roughly half evaporated, there's already too much noise in this thermal radiation, if Hawking's calculation is right, for the overall state of the universe to be noiseless, to still be evolving unitarily. And that's just because the Bekenstein-Hawking entropy formula says that the number of degrees of freedom that describes the sort of microscopic state of this black hole is proportional to its area in Planck units, the area of the horizon, And that already becomes smaller than the sort of entropy of this thermal radiation, even when the black hole is only roughly half evaporated. So that's where the real problem is. But there's a bit of a loophole here, which is already when that happens for something like an astrophysical black hole, then the amount of Hawking radiation we have is really, really, really big. In fact, it'll be something on the order of 10 to the 70 or more qubits for any realistic black hole. And that means the density matrix that you need to describe a thermal state of those qubits is really, 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 really big. In fact, it's exponential in the number of qubits, of course, so it's roughly 2 to the 10 to the 70 by 2 to the 10 to the 70 matrix. And what Hawking was really calculating when he did his computation is the individual elements of this incredibly huge matrix. And he was making approximations, he was treating the space-time semi-classically and so on. And so his calculation was only right up to tiny, tiny little exponentially small errors. And the problem is that those exponentially small errors can potentially turn a really, really noisy state into a totally noiseless one. Just if you tune the corrections in the right way, then you can only change each individual element a tiny amount, but still totally change the properties of the overall matrix. So what's the solution here? Well, this is where the sort of modern ideas from quantum information come in, which is just to do a direct computation of the noisiness of the state, rather than mucking about trying to compute the entire matrix before you start and then looking at the noisiness of that approximate matrix. So this is where we get to the exciting, new recent progress that's happened in the last few years. And what it really involves for the simplest calculation you can do is the most basic quantum information protocol for determining whether a state is noisy or not. And that's something called a swap test. This is something experimentalists will really use. And certainly theorists in quantum information will use all the time as part of quantum computing protocols and so on. But the way it works is really pretty simple. So imagine we have some classical distribution, some classical probability distribution, and we want to know whether it's noisy or not, whether it's just always spitting out some unknown fixed answer, or if it's doing some noisy distribution over all possible answers. If we only have one sample from this distribution, then there's nothing we can do and we can never tell whether it's noisy or not. But if we have two samples, then we can look at them and we can see if they're the same or not. And if they're not the same, we know that the distribution must be noisy, because if it's not noisy, we'll always spit out the same thing. If it is the same, then it's more likely to be fixed, because the probability for a very noisy distribution that we get the same thing both times is very small. It's much smaller than 1. So there's an almost identical quantum version of this, which is we're wanting to distinguish a very noisy density matrix from some pure state psi. And again, with only one copy of the state, doing measurements on one copy of the state, there's just no way to tell. But if we take 2 copies of the same state and do a measurement that measures a so-called swap operator, where we just swap over the two copies of the system, then we find that the expectation value of that operator is given by the trace of the density matrix squared, which is roughly analogous to this probability of the two states being the same for a classical distribution. For a pure state, it's always equal to 1, but for a very noisy state, it's much, much smaller than 1. So this is an experimental, practical way to determine whether a state is noisy or not, as long as you can produce more than one copy of it in some particular deterministic way. So let's say we try and do a thought experiment where we do this with some black holes. So we let them produce a load of radiation. I only drew one quanta there because I'm too lazy with my graphical skills, but we can imagine there's lots of quanta of radiation here. And then we're going to do a swap test on them. So what we want to do is we want to imagine swapping the Hawking radiation from black hole A with the Hawking radiation from black hole B. If we do that, we end up with this state where the radiation over on the left over here is entangled with the right black hole, and the radiation on the right is entangled with the black hole on the left. So in a fixed space-time geometry and just ordinary quantum field theory, this is a very different state from the state we had before. So that means the overlap with the original state is very small, and the expectation of this swap operator is much, much less than 1. So this is saying that the Hawking radiation is really, really noisy, and the more of it we have, the more noisy it gets. But in quantum gravity, space-time geometry isn't fixed. Instead, the Feynman path integral says we should integrate over all dynamical variables in our theory. And for gravity, that includes the geometry of the space-time, and it even includes the topology of the space-time. So you can have different bits of the space-time get disconnected and then glued together in different ways. So in particular, there's some exponentially tiny probability that there's a space-time wormhole forms, a shortcut through space-time that connects together these two black hole interiors and effectively swaps them over. This is just some dynamical process, right? I have by hand swapped over the two copies of the Hawking radiation, but then gravity, just by the inherent noisiness of space-time, has also swapped over the two black hole interiors. Then you'll notice that now this state looks utterly indistinguishable from the original state we started with, because the entire Hawking radiation and its entangled partners got swapped over between the two black holes. So the probability of this process is incredibly small, but it grows rather than shrinking as the black hole evaporates more and becomes smaller and smaller, and the space-time becomes slightly less classical. Turns out that the probability of this happening ends up giving the dominant contribution to the expectation of this swap operator exactly when we would otherwise have a black hole information problem. So rather than our calculations saying that the Hawking radiation just gets noisier and noisier and noisier forever, instead we see that it gets noisier and noisier until the black hole is roughly half evaporated. And then it starts getting less noisy again until when the black hole is completely evaporated, the space-time is very non-classical and the probability of this swapping of the two black hole interiors becomes order 1. And the noisiness goes to 0. Okay, so that's the main punchline of what I have to say. We do this experimental thought experiment that quantum information people would do, and we see that information isn't actually lost after all. It actually comes back. But I do want to emphasize that that was just a very baby version of the calculation. We can do a lot more than this. There's a whole literature of calculations and thought experiments and stuff you can now do, and they all end up being consistent with information coming back out of the black hole and no information. So in particular, we can compute the full shape of the famous Page curve, the entanglement entropy of the radiation. This was a prediction by Don Page in the 90s for what needed to happen to the entanglement entropy if we were going to have a unitary theory, if we were going to have no information loss. We can even use fancier ideas from quantum error correction, stuff from originally designed to protect quantum computers from noise when we're implementing complicated quantum algorithms. And we can see, in fact, exactly when the information in that book that I threw into the black hole back at the very beginning actually comes back out in the Hawking radiation. And again, our answers match predictions that people have been making, this case by Hayden and Preskel, for what should happen assuming that information doesn't get lost. But we're calculating them directly these days in gravitational theories. And just like for the swap test, the way the information gets out in this calculation is that the book somehow gets pulled through a space-time wormhole, and so its information comes out through that. And again, the key tool, just like the swap test, it's really a standard tool that people in quantum information theory have been using for decades. We're just applying it in a new context, and it's giving us these remarkable results that we've been wanting to have for decades and not having a clue how to get. So I just wanted to end my last couple of minutes by talking a bit about what's next from here. How is quantum information going to continue to influence theoretical ING physics? So I think because for 50 years we've known that the way black holes process information is somehow getting at something deep in quantum gravity, then it shouldn't be surprising to us that sort of some of the most prominent applications of quantum information to fundamental physics so far have come in quantum gravity, have come when studying black holes. But I really don't think they're the only time that this is relevant. Information theory really does give us a new way to ask about the things we've been caring about for a long time. So if you care about quantum field theory, if you care about maybe many body physics, more condensed matter, but still, if you care about the underlying theories that underlie standard model and all of particle physics, then you should be thinking about them in an information theoretical way. So if rather than just studying one correlation function in some strongly coupled quark gluon plasma, then we should be studying sort of how mutual informations behave, because those underlie all correlation functions. If we correlate, quantum error correction is not just some tool for implementing Shor's algorithm, even though that's why it was developed. it's a really fundamental statement about how information gets localized in quantum mechanics into different subsystems. And all of us should be sort of caring about it and having it as a way of thinking that is in the back of our minds. And even in quantum gravity, I think we're really just beginning to scratch the surface of what we can learn from these things. I've given a couple of examples here that are very biased to things that I've currently excited about and been working on and so on. But we're both applying sort of tools that have been around for decades in new ways to answer new questions in quantum gravity. And we're now at the point where we're sort of inventing new information theoretic tools because you know, it's not always going to be the case that Peter Shaw already invented what we need because he wanted to be able to factorize primes. Right? We have our own goals. We're going to need to develop our own tools sometimes, but the overall way of thinking about the problem, I think, is very deep and unique. And hopefully, our new tools could potentially be useful in the other direction as well, and feed back into practical quantum information theory, experimental stuff, and so on. So yeah, there's a huge amount of really hard conceptual issues that remain. I really want to emphasize that this progress on understanding information in black holes does not mean all of the information problem is completely solved and so on. But I just want to give you guys a sense of why a lot of find this very exciting times and why quantum information theory is really at the heart of that. So yeah, thank you guys very, very much. Yeah.
If there are any questions, please put them on Zoom or on the Google Doc. Quantum Gravity 8, half of the NQIS talk. So I will appeal to Paul Dabar to go faster for a good reason, by the way. It's really important. So without further ado, I'm going to give it to Paul. Jeff, go to bed. I know you're in Europe. It's late. Thank you.
Thanks a lot. Thank you very much for having me here.
Thank
really
you
great.
for this presentation.
Okay, great. Well, while that's getting set up, I'm going to be talking a little bit about what we were trying to accomplish in the National Quantum Initiative at the federal level across the various agencies, and kind of where we're at today. To use my Greek reference, if you look at Hegel, if you remember some of your quotes from Hegel, he gave a quote one time that said, "The owl of Athena flies at dusk," which is a reference to, you know, a little bit more about wisdom of a topic at the end of the day than you did at the beginning, right? Because you kind of live through it. And I think we've learned a lot since we were kind of trying to structure this in 2017 with a lot of people here in this room. So what was the goals of the National Quantum Initiative? First of all, was to add significant federal support to QIS. The Photonic Initiative and all the different kind of advocacy groups that were out there to say things were kind of reaching a point that an increased amount of investment would be valuable. And that was certainly, so getting money out the door and new programs was certainly the case. Obviously building off of efforts that we weren't starting from scratch. Myself, Walt Copan, head of NIST at the time, and Franz Cordova used to meet together on a regular basis around how to structure this and how we would structure the programs and how the various different efforts would be coordinated. Obviously, as you know, there was three verticals that we ended up structuring: the university support through NSF, the commercial industry consortium around NIST, and we'll hear about this from Carl here, who led that up, and the 5 R&D centers that DOE ended up bidding out. There were very specific things we asked Congress to pass when I went to go testify and help write this. But we wanted to have diversity of parties. We wanted to have labs, universities, and the private sector in each bid. That was a requirement. First time we had a significant scale of private sector in an Office of Science major research program. And there were some very interesting parties, I think, as everyone knows from Joe's layout, you know, companies like Rigetti and Applied Materials and even Goldman Sachs, right, and IBM. We wanted to trigger additional interest and investment. Boy, that worked. I'll get to that in the next second, on the next slide. And then try to coordinate future quantum efforts at a federal level across different agencies. So that was the goal of what we were trying to get done. So what happened after we launched it? Well, we got quick and full support from Congress, including appropriations. We got all the money very quickly, first year, which doesn't always happen in Washington, after the authorization bill under the NQI was passed. We spawned derivative efforts, right? Even things that were really not part of the National Quantum Initiative technically. So the Quantum Internet Blueprint was really a derivative of the NQI efforts and people getting together, talking through that. The three agencies executed very quickly on their verticals. The NQI centers, for example, were bid out very fast, but actually NSF got theirs done before even DOE in terms of the university program. So that worked very well. We got high continued interest from all sides in Congress. This is incredibly topical. We can maybe talk about that as appropriate with the panel, but I spent a lot of time with Senator Schumer that ended up with the Endless Frontiers Act, which is highly engaged, as everyone is probably following right now, because the EFA kind of morphed a few times, but it has a massive increase for HEP embedded in the DOE for Science Act that's now part of the overall bill. And I think that's a really big theme, okay, around what one of the primary purposes here was, that derivative technologies that could spawn new industries, spawn interest in discovery science. Okay, that's probably the most important thing I would love everyone in the HEP community to understand, which is, someone who spent their, time in my last job trying to get as much money for everyone here in this room, okay, as well as NP, wherever Stuart is, as well as Oscar, as well as BES, trying to get as much money as possible for every single community, but including HEP, was how do we build a consensus? How do we build broader support and new industries of the future that have technologies that could lead to new things, new jobs, new economic impact, is a way to get HEP money. And that was reasonably successful, I think, with the budget increases during the timeframe. So that continues. Where's the jury still out from what we were intending? I think community building needs to continue to happen. The quantum community is, there's been a lot of effort, but I think there's more that can happen. The science and technology achievements that the funding happened is obviously still early stages, but I think what's really important, and Harriet and DOE does a good job of holding people feet to the fire when they got a grant and it's 5 years later and it's time to see the paper, it's time to see what you promised, and going back and taking a look at it. I think that's an important kind of focus. The impact of NSF and DOE efforts on commercialization. I think the NIST efforts is quite obvious, but does NSF or DOE efforts have an impact on that portion? So both the science portion, which is the one up above, as well as the commercialization one. The new administration, will the new administration grab any additional programs? Certainly the Senator Schumer's big act, the CHIPS plus whatever we want to call it act, could be the trigger for this. So we're certainly focused on that right now. And potential what I would call national projects. That's something that could be next. So what could we do in terms of a first quantum advantage QC, right? An HPC, maybe it's a heterogeneous machine as we were talking about earlier. Quantum networks. I think we should all be very positive about DoD. DoD just jumped NSF and DOE and announced the first quantum network for DC, first one in the world. And I think we should all be very positive about what DoD has decided to announce and tried to build the first one in DC. But could the act trigger 3 to 5 other ones around the country? I think we could very easily see first metro area quantum networks in the Bay Area or Chicago or New York, greater California as part of that bill, and assuming it gets funded. So these are things that are big national projects that could easily move forward. And then the status of the quantum tech community. There's been an explosion, frankly, of lab and academic and commercial efforts since we started this thing in 2017. The expansion of university programs, I think as many of you know, massive private capital investment in this sector. Okay, that's a long conversation that I do not have time to go through that here today. But one of the things that I would say when I was before Congress is that that federal spending should be the trigger of a new industry, of new technologies that would draw in venture capital, draw in others, and boy, did that work beyond my expectations. Glad to see that support. There's some challenges right now because of what's going on in the markets and the tech pullback, but notwithstanding that, it's still far higher than what we were expecting. Private companies are now under the focus of investors to deliver in a timely manner. I think as those of you who are following companies like Rigetti and IonQ and others, but even people who've done private rounds, they promised that they were going to deliver something in a certain period of time. And when you have the discipline of a private market where, which is far, frankly, tighter than the science community, you said next quarter you're going to deliver on X. And if you don't do it, it's quite painful. And so that sort of discipline for this sector is about to hit. And there could be some painful kind of outcomes, right? But this is all part of the process of something kind of being pushed forward. Certainly, greater awareness by the political community. And I was talking about Senator Schumer's bill, but the view of technology and industries of the future has really grabbed, once again, a much longer conversation, but the political kind of groups, and especially in DC, are much more interested in how technologies in biotech or AI or microelectronics or quantum can have an impact on industries of the future. And they're very willing to invest, around that. Sorry, the other way. And then the last page here. So what do I see about the kind of the continued interaction, right? The growth of the interaction that we already engendered between government / national labs, academia, and the private sector. So the quantum tech world is still a bigger gap than some other industries in terms of where the science community is and where the use case community is. I'll take biotech. Biotech's been doing this for decades, okay? It's a very well-aligned industry of where NIH comes in, where they fund an early stage PI, and how that transitions into a biotech drug and how venture capital then funds that. That sort of continuity is well developed in the biotech community. The quantum community, between high energy physics all the way to useful products, needs, and that thought process of people who come from different angles needs to come together. It's important to start delivering on something from that point. For those of you not familiar with the energy tech space, there was a big rush in energy tech, a lot of like bioenergy in the 2000s. For those of you who maybe have been at the national labs, they all failed, okay, for the most part. And the venture community for energy tech collapsed for about 10 years. Because people promised that they were going to deliver on bioenergy and energy tech. They didn't deliver, and the venture community just fled. And so it's important that as momentum builds, that there's some wins with energy. Sorry, with quantum technologies. QCs are the obvious one, but there could be others. I'm a big believer that government should be a first purchaser. I think a national lab should be the first purchaser of a QC or a heterogeneous QC with QPUs. I think DoD and NASA should be launching a satellite. I think it's really too bad that we haven't already in the United States. And I think the metro area quantum networks, as I was talking about, needs to be driven by the first ones by some of the government efforts, just like NSFNet was back in the day. And then the last thing that I would say is that there needs to be some real international collaboration. I've spent time in DC where, a lot of the quote international collaboration is, someone at the White House signs an MOU between this country and that country, says we're going to work together on that. And then it never actually turns into a project. Okay, that's a lot, okay, of what happens actually between countries. And so we actually need some real international projects with real programs, just like we would do domestically here in the US, and with real money attached to it and real goals. And I would advocate that we figure out how to do that. So, Maria.
So Paul will sit in the panel so you can ask him questions, but let me ask the participants of the panel to get up on the stage, the ones who are here, And the ones who are remote on Zoom, please turn on your cameras, and we're gonna put the initial remarks up, and we're gonna keep it at 2 minutes per person, because we have a strict limit on the cutoff time for this room. We cannot keep the room. Okay, great. That's great. So how can we fit in the screen them and the slides is my question.
Yes, 1 second.
Maybe we put them on a vector instead of a matrix.
Yeah.
Hello, hello. Check, check. Can you hear me? So shall I just proceed, Maria? Oh. Hello?
Yes.
Hello? Okay, good. Thank you.
Actually,
How many people are on the panel that are on?
they are the ones on the with the Zoom on their video.
Okay.
So
these people as well.
except for UC Irvine, who is on the video but is not on the panel. But you can stay on the video. We just want the panel people on the video. No problem.
I thought there was the question section. Sorry.
All right, great. Thank you. Now, people should be, all of them should be on the video, but I wanted on the top of the list here to be our panelists. And when we can scroll on them and put them when their turn is.
Who's first?
So we start with Aaron.
Okay, hi. I'm just going to be very quick here. I want to talk about this concept of using a quantum computer as a dark matter detector. And I just have 2 really quick things to show. One is the research that we've been doing at Fermilab as part of the Quantize program with collaborators at University of Chicago. And the idea is we know that quantum computers are made out of qubits. Qubits are nonlinear oscillators. In some sense, they're artificial atoms. But for this high energy physics community, I want to draw your attention to this picture here, which is a single superconducting qubit that's living inside an open aperture microwave cavity. And it turns out the physics of these qubits are exactly the physics that we're familiar with from neutrino oscillations, in the same way that an electron neutrino can sense the presence of the background electrons that is passing through by a perturbation to its mass that you see through the oscillation experiments. This qubit in here, living inside the cavity, can sense the presence of microwave photons, single microwave photons that are living inside the cavity. And the cavity is actually what was called a quantum RAM, random access memory. So you load the initial data of the computer as single photons in this quantum RAM, and you manipulate it through the interactions of the superconducting qubit. All you see are the antennas with the RAM, and that's how you sense the presence of the information. And the idea comes from this old idea of single event upsets in silicon-based computers, where cosmic rays or other ionizing radiation flies through your silicon computer and creates an error, causes your computer to crash. We're quite familiar with that from our high energy experiments. And the same thing happens here. We have this quantum RAM. We loaded the information of our program into this quantum RAM, and we're going to manipulate with qubits. If we didn't load any information, sometimes the dark matter comes in and loads spurious information for us. We check for qubit errors, and from the rate of the qubit errors that we see from the cosmic rays or dark matter flying in, from that rate, we can directly infer at this point limits on how much dark matter might be passing through. And it turns out these limits, oh my God, these limits are very competitive with the best dark matter experiments that we have today. As you can see this, okay, we'll go to this slide. The second way in which the qubits can also directly sense the presence of dark matter is that the qubits are living on substrates typically made of sapphire or silicon in exactly the same way as one of our solid state dark matter detectors like Super CDMS are living on silicon substrates that serve as the target medium for the dark matter. So again, we have ionizing radiation flies through, deposits phonons, sometimes it deposits charge, and that charge can be sensed directly by the qubits. This was not noticed by us in the HEP community. This was noticed by Google in this famous paper from McEwen, who was a student of John Martinez, who actually was a collaborator in Super CDMS. And they noticed that in their Sycamore computer, this is a pattern of qubits, they noticed that at a 10 microsecond rise time scale, cosmic ray flying through will cause 100% qubit failure across the entire chip as the event spreads across the entire chip and recovers on a time scale of 25 milliseconds. Okay, so the idea here is we're going to be using these quantum computers as very sensitive photon, phonon, and charge sensors for our dark matter experiments. Thank you.
Thank you, Aaron. Monica, you're up.
Thank you. So I think many of us here are motivated, at least in part, by the quest to sort of understand the fundamental building blocks of nature, which I've is sort of epitomized by this quote from Democritus, the Greek philosopher, who tells us that these things like taste, sweet and bitter, temperature, hot and cold, color are what he says by convention, but in truth there are but atoms in the void. So this is sort of saying we well understand today that sort of macroscopic behavior like taste and color and temperature emerges from microscopic configurations of individual atoms. At the time, this was a revolutionary idea. These days, one can actually manipulate even individual atoms and observe them in the laboratory and potentially even use them as building blocks of quantum computers. But one of the sort of remaining mysteries today is really fully understanding that second part, the void. So for example, is space-time really smooth, or do curved space and gravity also, are these also phenomena that really emerge from some more fundamental discrete constituents? And I've illustrated that concept here with a picture where, for example, perhaps the discrete constituents are qubits, and what we see as curved space with gravity actually emerges as a description of the quantum correlations or entanglement between them. That's shown here by these white lines that are giving rise to essentially some extra dimension that actually looks, in this case, like some discretized version of a hyperbolic space. So this is an example of an idea known as holographic duality that is one theoretical concept of quantum gravity that's actively studied theoretically, but are these ideas that might also be possible to explore in the laboratory? So if you'd like to start answering questions or testing ideas about quantum gravity in the laboratory, if you'll go to the next slide, there are a couple of different approaches that one might take. And in particular, two sort of powerful approaches that I'll mention are either precision measurement or quantum simulation. So in the idea of precision measurement is, can one build systems in the laboratory that are extraordinary precise measurements that are sensitive to both quantum mechanical and gravitational effects. So examples would be atomic clocks made of atoms in quantum superposition states, which are sensitive even to the gravitational redshift associated with height differences of a few millimeters. That's one direction explored in state-of-the-art research. On the flip side, so that's sort of trying to directly test and measure and precisely probe gravity in our universe. A second approach is to ask, based on this elegant theoretical idea that gravity might be an emergent phenomenon, could we start from the putative microscopic building blocks, individual quantum mechanical degrees of freedom, and build model systems in the lab where one might ask, if I measure correlations or entanglement in this system, can I see something that looks like curved space or gravity emerge from that microscopic model? And in my lab, we're actually exploring contributing, I would say, to both of these directions, where in both cases sort of one can benefit from well-engineered quantum systems, where one has, for example, a high degree of control over interactions between, we work with laser-cooled atoms, and those interactions can either give rise to entangled states that can enhance the precision of these sensors shown on the left, or perhaps be the building blocks of this phenomenon of gravity emerging from quantum correlations. And so on the next slide, I've just shown kind of one illustration of a recent experiment that we've done, if you'll flip the slide, that was taking the latter approach, asking, can we simulate, to start with some toy model of this idea of holographic duality. And so this is something where we built a system with atomic ensembles that can talk to each other in a very well-controlled way with the aid of photons in an optical resonator. And we realized a structure of interactions that gave rise to correlations that we can measure in the lab. Actually, by measuring those correlations, we found that actually what emerges as the natural description of those correlations is this tree graph, which can be viewed as actually a discretized version of a hyperbolic space. So that's sort of a first illustration of trying to connect really sort of tabletop quantum experiments to these remarkable ideas that have so far been sort of hitherto confined to the realm of theory, that gravity and curved space might be emergent phenomena. And I sort of presented this from the lens of asking what can quantum systems do to help us understand this high energy phenomenon. But you can also flip this around and ask, actually, can these theoretical ideas contribute to our understanding of quantum systems and give us new ways of visualizing and understanding this phenomenon of entanglement that ultimately is going to be at the root of quantum technologies?
Thank you, Monica. Anna, you're next, all the way from Italy.
Hi, good afternoon, good morning from Italy. Can you go to the next slide, please? I'm very excited to have just 3 minutes to tell you about this new quantum center. You heard from Paul Dabar how exciting this 5 national quantum center that DOE is funding. We are the Superconducting Quantum Materials and Systems Center. We bring together more than 23 institutions, more than 400 researchers. The center is led by Fermilab, and it really embodies this idea that Paul told you about of bridging the gap between university, national labs, and industry, really bringing together all these experts in a multidisciplinary type of collaboration to make revolutionary advancements in quantum information science. If you go to the next slide, our center, really imagine this center as mini Manhattan projects. We are really doing this actually, especially the Fermilab-led center. We are very mission driven. So we bring together all these collaborators, not in a sort of like funding agency type of environment where different, disconnected small efforts, but really we are brought together by ambitious goals. And in particular, we want to develop a Fermilab, the first quantum computer that will be actually built by our people and will be based on our technology. So we are world leaders in superconducting RF cavities. We have demonstrated that they can be the best quantum memories with 2 seconds of coherence in the quantum regime. And because we have this core expertise, we actually bring it to the table, to the field of quantum information science, to build a quantum computer based on this architecture. So this is our ambitious roadmap. We are going from few qubits all the way up to potentially 1,000 qubits and a quantum computer Fermilab. And the roadmap goes through a lot of technological innovation hand in hand with academia experts and with industry, improving coherence time of the building blocks like transmon qubits of these cavities. And also at the same time, we actually take these building blocks of a quantum computer and we deploy them also as quantum sensors for fundamental physics. So of course, because the center is led by Fermilab, we have a very strong mission and flavor of utilizing the quantum computers that we develop for our own mission of understanding the world of particle physics, and also in the quantum sensing. Yes, please, the next slide, thank you. So I just wanted to give a little glimpse on the quantum sensing area, why these centers are so unique and so and so beautiful, actually. This is one of my favorite parts. We bring together in a co-design framework, really experts from many, many areas that put together, they can advance experiments otherwise wouldn't be possible. So here you see an example where these cavities with qubits can be single microwave photon counters, so actually they can really exclude potentially dark matter, dark photon with the best sensitivity. But how do we get to this? Is by putting together the best theorists, the best experimentalists, the best experts in materials, in prototype of superconducting devices, and all together in co-design, we advance new experiments. So we have a very rich physics program, which I don't have time to talk about, but we are very excited that thanks to the technological strengths that we develop for high energy physics, we now can have an impact in quantum information science, but also this can come back to us for our mission of particle physics.
Thank you, Anna. And thank you for joining all the way from 3 a.m. Travis, you can
Hello. Hi, everyone. I'm Ravi Nayak from Berkeley Lab. And I just want to give a brief overview of some projects that we've done in the past involving quantum gravity and quantum information science, and then also talk a little bit about the advanced quantum testbed. So first, I'll start with this paper and experiment that we did a couple of years ago involving quantum information scrambling. And in particular, we are using ternary quantum logic to distinguish it from our standard sort of qubit processing. If you consider sort of a thought experiment, a Hayden Preskel thought experiment involving some of the experiments that Jeff described earlier, it turns out that we can actually map this problem onto a simple quantum circuit, and actually an efficient quantum circuit if we consider our fundamental quantum units to be Q trits or 3-level systems rather than Q bits. And that circuit is shown over here. We were actually able to execute this circuit using a superconducting Q-chip processor that we developed in our lab. Here you can see that we can have high fidelity distinguishability of 3 quantum states for measurement, and also the ability to create highly entangled Q-trit states. And the primary piece of this puzzle is the scrambling unitary that describes the process of quantum information going through this wormhole and exiting as Hawking radiation. And the scrambling unitary is shown up there, where localized quantum information is mapped to highly delocalized quantum information. And we were able to show that we can actually demonstrate scrambling beyond the limit to show that we're actually demonstrating the scrambling when we do this teleportation experiment here. And this is sort of an early experiment, if you go to the next slide, as part of our advanced quantum testbed. This is a new creative research laboratory at Berkeley Lab. And we have a user program where we can we accept proposals from any user that's available, and you can accept proposals. We can send proposals at our website shown here. After reviewing the proposals and finding the ones that are most appropriate for our platform, we engage in sort of an active collaboration with our users. And we have a full stack platform, including software, custom FPGA controls that are actually part of the quantized program, cryogenic platform to control the environment of our processors and the processors themselves. Just to give a flavor of the types of programs that user programs that we engage in, I have one example, which is a collaboration with Sophia Coaglioni's group at Livermore. And here we're investigating a hybrid quantum classical algorithm, which is a very popular flavor of algorithm for NISQ-era quantum computers. And here we're studying the evolution of interacting neutrons. And the hybrid algorithm goes as follows, where we use a classical computer to propagate spatial degrees of freedom. And we use the quantum computer to propagate the spin degrees of freedom. And we do this for each time step and track the trajectory of the quantum spins of the neutrons. And here's some early data shown right here. To derive this data, we've gone through several steps involving all the steps of the quantum stack, including extensive error mitigation to reduce the errors as much as possible, something that's very important for near-term quantum calculations. Thank you.
All right. Travis?
Well, hello, everyone. It's a pleasure to be here. The intersection between high energy physics and quantum science and technology is, of course, a very exciting area. The part of this intersection I would like to talk about is the culture that emerges, especially the culture around quantum computing. I think we can all recognize that there's multiple technical reasons for why these two fields crisscross. But the idea that quantum computing as one of the more easily identified and conceptualized outcomes actually speaks of something common to both the principles of science in both fields, as well as in the cultures of the disciplines. And I'd like to highlight 3 of these things. One of them is the paradigm of quantum information. I think this is the easiest one to accept. It's the realization that the encoding of nature based on quantum mechanical concepts themselves actually has profound impact on our understanding of what's being done. The second is the intimate connection between the technology that's being developed and its scientific drivers. I think this is something that the high energy physics community will be familiar with, but it is something that the quantum computing community is just beginning to learn. As was discussed earlier, this has been a very rapid growth in the field of quantum science and technology, and realizing exactly how this will play out over the coming years is going to be an important part in its development. The intersection with HEP could have a profound influence on that development. Finally, there lives within this intersection a promise for surpassing our known limits. That is something that I think is fascinating. It's one of the key outcomes that we hope to be able to take advantage of, especially in new modes of discovery and innovation. So of these three priorities for the intersection, I'd like to talk just a little bit more about the second in the next slide. This connection between quantum technology and its scientific drivers is more than just saying, what are the purpose of using quantum computers for high energy physics? Of course, modeling and simulation, data mining, machine learning, all of these application concepts can be mapped on to the HEP problem space. But there are other key concerns, such as the software systems, tools, and techniques that underlie the use of these technologies, as well as the networks, the workflows, the interfaces, and the infrastructure that will be necessary to make it impactful on the science. So moving forward, I think this intersection needs to recognize that connecting the technology back to the science itself is going to be pivotal to delivering on the key outcomes that we all hold promise for. So thank you very much.
Thank you, Travis. Yes, Krista is next.
Hi, everyone. I'm Krista Savori from Microsoft. And I want to focus on the intersection of high energy physics with quantum computing in particular. As we just heard from some of the other speakers in this session, there's the potential for quantum computing to help solve some of these very challenging problems, intractable problems across high energy physics. And what I'd like to make sure to share is that over more than a decade of research at Microsoft, we've come to understand that impactful applications, right? Applications where we really are enhancing our scientific understanding and we're seeing practical, useful solutions coming from quantum computers, they do require upwards of 1 million physical qubits. And so we need to look at applications, first see, can we find applications, perhaps across high energy physics, where we can have smaller scale machines? Where can we find applications that help enhance our scientific understanding? And as we scale out, that technology leadership will require physical qubits of upwards of 1 million. So at Microsoft, of course, we're working to build such a machine and integrate it into Azure. And already today, we have a diverse set of quantum machines in Azure through our Azure Quantum platform. Now, when we think about these applications, I think it's important to understand how these applications work. And we heard in one of the earlier talks just in this panel session that these applications are hybrid. So if we go to the next slide, I want to encourage this community to think about what those high performance hybrid quantum computing applications look like. And they really are hybrid, right? In this diagram, this is an example of a quantum algorithm for catalysis, where what we want to do is we want to have massive exploration of, say, materials and structures. And for that, you need a supercomputer, a cloud compute capability like Azure, where you're exploring different catalyst structures, for example, modifying those structures. And then for a given reaction pathway, you're asking the quantum computer to do something more accurately. For example, in this case of catalysis, you'll be sending to the quantum computer and asking the quantum computer to do an accurate energy calculation, sending back continuing a search over, and then repeating this many, many times for the different reaction pathways. This can help you find and understand a given catalyst in a given reaction. Now, similarly, I think across high energy physics, there's a lot of potential for identifying where can we bring together AI, machine learning, data mining, as Travis just mentioned. How do we bring that together with quantum computing to advance the state of the field? And you can try some, try programming some of these algorithms today in Azure Quantum, which is on the Azure cloud and open source and ready for you to come try and free.
Thank you, Krista.
And that's it. Thank you.
Thank you very much.
Good, thank you. I just wanted to give you, not actually tell you about my own research, but just give you a little bit. I talked with many of you during the last few days. And the question is always, why should we in HEP care about quantum computing? So I just wanted to make that case in like the next 2 minutes. So this is, can you stay on that first point? Yeah, so that's a plot you've probably seen a lot that sort of shows somehow a classical computer performing poorly, right? There's a sort of a straight line if I plot computing power logarithmically, and then you see that plot where quantum computer just exponentially ramps up, and then everybody says, great, quantum computers will outperform classical computers. The next slide. The important question, though, that all of you should actually ask, do we have a problem in high energy physics that we actually care about where the quantum computer can do this? Because you should realize the quantum computer will not perform better on every single calculation. And you can make this argument on complexity classes. There's sort of a class of problems called BQP, where quantum computers can do this in polynomial time, and P is the class where classical computers can do that. So we need to make sure that we have a problem in high energy physics in that blue area. And so if you go to the next slide, there is actually, and the important thing is that there are such problems. And I think what is even more important, these problems are really foundational. They would really change how we would do particle physics. If you go to my last slide, second to last. So this is the important message. These problems exist in many areas of HEP, and in our white paper that we wrote, we've actually identified many of them. And so let me just give you one example here, which I think most of us would agree that this would really change how we do particle physics. Namely, if you could do a first principles, a non-perturbative simulation of the dynamics of a quantum field theory of SU3, let's say, we could really go and just compute the things that we have no way of doing these days. And this problem, for example, is shown to be in this class, where quantum computers will eventually outperform a quantum classical computer. So my last slide. And so to me, of course, this is not a proof that a quantum computer, say, in our lifetime can do this, but I think this should be enough motivation for us to go and actually do the hard work that is required to really see if, how, and when this can be done. And there's a lot of theoretical work that needs to happen. We need to work together with the people who build quantum computers. So I think we really need to spend the efforts in the next decade to see how we can do this. And I don't know why I repeated this. There was supposed to be another sentence in here. But the message is we really need to spend the effort to do this. And I think we need to start this now, because even if someone would give us a quantum computer today, fault tolerant, it would probably take us 10 to 15 years just to develop the theoretical tools to actually put these calculations on a quantum computer. Thanks.
Thank you, Christian. And on the Zoom, we've got Sanjay from Brookhaven.
Thank you. This is Sanjay. So here is I want to pitch on the how could be quantum machine learning can contribute on the high energy physics. I think in the beginning of the Joe already mentioned some of those aspects. So let me be more brief. So we have many high energy science, high energy physics drivers experiment, and then we already seen the tremendous success on the high energy physics in the machine learning application. But on top of that, however, the sensing technology and the simulation need keep increasing. The demand keep increasing, and then that driving higher volume, higher velocity. And also, this is high energy physics handling particle physics data. So it tended to be more sparse data than the regular AI ML community data. So quantum machine learning, if we can bring some potential quantum advantage to this high energy physics data challenge, we could potentially see some, let's say, exponential or quadratic speed up. Next page, please. Next slide. Yeah. So we already applied, and then many of the quantum machine learning community working with the high energy physics community together, we demonstrated, however, some of the early success, but it is still quite limited, largely because there is many hardware challenges, and also some of the simulation if we want to do due to the limited the coherence time. But we believe the better simulation software are keep coming up using the, for instance, supercomputer scale, the simulation software. And then the brighter roadmap. What I meant is that I've seen the roadmap from the IBM 1000 qubit next year, although it is not error corrected, but the IonQ and then the Google error corrected 1000 qubit by 2029. And then also there is some technique we can do immediately, as other panel mentioned, quantum classical hybrid approach. Some of the problem we estimated that we may need a 10 to the 5 qubit, but with those kind of technique, we can starting solving like with the 10 to the 3 qubit. And also the other great opportunity to me is given the quantum sensing and the network technology development, jointly working together with the quantum machine learning, I think it might be a great opportunity to consider. Thank you.
Thank you. Thank you very much. So the panelists on the Zoom, please stay there. We are going to have about 10 minutes discussion, and then we're going to close with some comments from Kel Williams. So let's hit the discussion with already a question from Zoom. Martin, could you tell us the question? It's from Irvine, or if they want to voice their question, they can do it and then address the panelists if they have a question for a specific panelist or speaker for that matter.
Either way is fine. I think the audio is not good from us, so you can read it. I think I type it, or I can read it as well, depending on which audio is better.
Why don't you just go ahead and try and ask the question and see what happens?
Yeah, thanks. And sorry for the previous, I thought there was the questions here. So there are exciting space version of the quantum sensor studies that parallel to what Joe described. For example, one can have this. So for example, one can use the NASA Deep Space Atomic Clock combined with space missions to search for ultralight dark matter and variation of fundamental constants. So how do these space-oriented projects that are kind of independent from our current quantum programs, how can we feed them into this quantum program and also feed them into the SNOMED efforts? Thanks.
All right, so I will repeat it from, I will repeat the question. There are exciting space versions of the quantum sensor studies parallel to what Joe described. For example, one can use the deep space atomic clocks combined with space missions to search for ultralight dark matter and variations of fundamental constants. How do these space projects tie into the quantum programs that Joe described and to our SNOMED efforts? So I think this is for you, Joe. And maybe Paul DeBar can comment as well, because he included that in his talk.
Yeah, I think there's two things I can say about that, and Paul may have something to add. So one is we do have collaborations already on quantum with NASA JPL. I showed a picture of Matt Shaw, who's the guy that makes the world's best SNSPDs, which are very, very important for multiple collaborations we're doing. So I think at that sort of scientist to scientist level, then their NASA collaborations are already happening. Then at the sort of higher level, I think there has been a push, fairly recent push, for DOE and NASA at sort of the agency level to be talking about doing, real collaborations and kind of looking to the future, as NASA is now ramping up a bunch of new things and understanding how we can work together better. So maybe Paul has more insight on that.
Yeah, I mean, I could comment that Europe's obviously announced a very large QKD satellite proposal. It might be a little bit delayed given everything that's going on, but that was a extremely large announcement on a satellite deployment for QKD. Obviously, there was a historical one on kind of the science proof case that China did. You know, I think the U.S. needs to be pushed harder to be direct. I think the European announcement should hopefully kind of get people thinking about the U.S. You know, doing that. Obviously, there's a bunch of debate on the value of QKD that our friends at NSA have been publishing. If you haven't been following that, on the efficacy of QKD, that's a controversy out there. But I think jumping all the way to entangling quantum data, which the SNSPDs and so on would have as much efficacy for space deployment as it does terrestrially, is something that I think the U.S. government system should be pushing.
Thanks.
Carl, I see you unmuted. I think you have many things to say here, so why don't you?
So let me say a few things, and you know, whether QKD has value, it is the simplest quantum communication protocol to implement. And you know, the first thing you do is you implement that protocol. I think it's point to point, and I think it has little long-term commercial value. But it is the means by which you begin the whole quantum communication, quantum networking process. So I think it's something we should really strongly support. You know, and you know, with regard to a couple of the talks, you know, I think what's tying physics together across the whole realm is in the fact that we now know today that information is fundamentally physical. And that ties and brings physics back together in a way, you know, from the end of the 20th century, end of the 19th century, physics diverged into multiple fields. We are coming back together because information ties us together. And it doesn't matter whether it's condensed matter physics or high energy physics or cosmology, black holes. We've heard it all here today, whether it was from Geoffrey or Paul or anything else. So I think it's exciting times. I think it's very important. I think it's exciting that, you know, recently you saw Junyi basically see the curvature of space-time at 100 microns in an atomic clock. Right. I mean, who could have imagined this? I mean, this is beautiful physics, and it shows that AMO, GR, and high energy physics all have a unity behind them. Right. And it sets a future for physics that I don't think has been seen in 50 years.
Thanks.
Somebody needs to mute. Okay, oh, Carl, okay. All right. With that, let's take some questions from the audience here. Yes.
Thank you. I have a question to Paul Dabar. I mean, with this, you mentioned about the need of not only signing MOU, but having some strategic projects. But I mean, if we go beyond the single country, in the current race, which we have, do you see a way based on your experience that the nations can work in a consolidated way, taking into account that the challenges and priorities in different countries is different? We've heard today about the high energy physics. One can imagine this can be applied to climate, to financial markets, but still, I mean, what you've seen in DOE and also in the Congress, is there a way, to your opinion, to proceed even with the alliance nations to try to build a global community in some of the areas, and how?
I guess this is a question for Paul to start with. Yeah.
Yeah, so I clearly think that there is, and it needs to be a whole lot more organized than is going on right now, including when I was there, right? I think that needs to be pushed forward. You know, as you think about the value of quantum technologies on a national basis, and because you have to think about that first before you talk about international. You know, there's support for HEP and there's support for the other programs in science. The base interest is from the politicals that usually have a university or a lab in their district or state, right? That's not enough interest to get support for the level of support that everyone here in this room wants to have. Layer number two, to get more political support, is will potentially technologies that are being developed as a spin-off, as a result of discovery science, have value. I mean, the biggest one here in the room, right, is a World Wide Web, right? I mean, that's the biggest, you know, victory of the HEP and Cern, but there's plenty of others. And so you want to get a political class kind of around that. And then the last one is national security. And the reality is there's a complicated history of the physics community and national security, but it's there and it continues, right? Notwithstanding anyone's individual's kind of view of that, it's a part of the history and will continue to be part of the future. So if you layer in all of that, right, and you talk about international cooperation, I think there is ripe support with, you know, I come from a political job, even though it was a science job, but it's about who you have partnerships with. And I think when you think about this as the United States, there is strong support for the vast majority of the countries in the world to try to do some work, starting with basic science and discovery in quantum. But, you know, as it evolves into potential economic, and then finally as it evolves into national security. So I think that there's a vast amount of countries, basically every place in Europe, okay, large swaths of Asia, right, who are part of that economic and even national security aspects. So there's a wide opportunity that we have not, you know, speaking on behalf of the US here, we have not, you know, engaged with, you know, strong people that easily fit into that. And I think there's a lot of specifics that could happen.
Thank you. We have a couple of questions on the Google Doc that Martin will read, but first we're going to read some prepared remarks from Carl, who was, we didn't know if he would make it, yes or no. And this is 3 minutes, and we will continue with the questions and close.
So high energy physics and general relativity are about answering the most fundamental questions in physics.
We're going to take it after.
And the experiments and theories are among the most challenging. Perhaps not surprisingly, they also have been impacted and have impacted QIS. So for example, LIGO now uses squeezing. It uses some technology to actually do some of the most sensitive experiments around. But these fields also require the best technology and have long impacted an advanced technology in order to perform the experiments necessary to test these fundamental theories. As a result, they will both be early adopters of QIS, and they will help develop the quantum information science and technology further. The early demos of this has been the observation of the effect of the curvature of space-time in an atomic clock, an experiment recently performed by Junyi at Gila and NIST, where over a distance of a micron, he can actually see the impact on the clock. It is absolutely remarkable, and I am sure there will be many more surprises as we move forward. Today, QIS, its informational theoretical approach, is being used to help bound future theories involving the unification of quantum mechanics and general relativity. Again, a place where HEP and GR come together. So how will QIS impact high energy physics? And now we have to begin to speculate just a little. Well, perhaps better detectors, better timing, more sensitive, faster, better classical and non-classical correlations, perhaps coming up with better theories to test, perhaps more stringent bounds on the neutrino's mass, or perhaps the discovery of axions or other exotic matter. All these things are relevant to the ultimate theory of the universe. I am not a visionary, but there are some, like Richard Feynman, who could see into the future. And Richard Feynman helped. In fact, some people would say perhaps he is the father of quantum information science. So high energy physics, general relativity, and QIS have long intersected and will continue to do so. QIS in the ultimate theory of the universe, that includes where HEP and high energy physics and general relativity intersect, have long had historic connections. And so it is important as we go forward to think about this. Feynman impacted so many fields of physics and clearly is the father of QIS. So how does high energy physics and QIS impact each other? I believe they will increasingly move in lockstep by enabling one another. Not only high energy physics and general relativity that are impacted, but you see this in condensed matter as you look at critical phenomena and everything else. And so since the 1920s or 30s, physics is basically spread out into different subfields. And what QIS is doing is bridging across those subfields to bring things back together. The information theoretical approach and everything else is helping define the ultimate limits of these theories and everything else. So I think it's a remarkable time in physics, and it'll be interesting to watch the next 20 years.
And since we do have Carl, I want to thank him for these remarks, and we'll get back to close. But first we had one more question in here, and then Martin has two more questions on the Google Doc. 2 minutes. 2 minutes. We have 2 minutes for one question. No, do it. We have 2 minutes. 2 minutes is 2 minutes.
Sure. Okay. So my understanding is the government's interest in quantum initiatives really has to do with, you want a quantum computer, you want quantum networking for security.
Speak up a little.
We can't hear you.
So my understanding is that the US government is really pushing for these quantum initiatives because they want a quantum computer and they want quantum networking for security, international power reasons. As a particle physicist, I'm interested in understanding the, fundamental particle content of the universe. I think sort of related to the work Aaron's doing is like, it would be great to discover axions. I don't care if you use a qubit or not to do it. For someone who really knows very little about quantum, could you make a connection between those two very separate goals? How does Aaron's work help the US government get a quantum computer if the work that we're doing as particle physics doesn't satisfy the US government's goal? Are we at risk of having that funding cut in the next 10 years when they reevaluate their programs?
So I will be the eavesdropper on this communication channel and drop it, because I will ask Paul Debar to go on the Google Doc and answer this precisely, and we are logging it down. Happy? Because otherwise, this gentleman here is going to kick me bad.
Although, just come down.
Or you can talk as we close. We're closing. Carl wanted to say a greeting.
No, I just want to come back to this question. I think the government, if you look at the NQI, and Paul Debar already talked about it, the NQI was about building a workforce to support future technology. This technology is going to be the basis of everything.
Carl, we're kicked out.
Okay, I was just going to say, final comment is science is important.
All right, that's great. Thank you. With that, we close. Thanks to the panelists, everyone who came from the outside, Monica, Anna, Sanjay, Krista, Travis, and Martin, of course, and everybody else. And thanks everyone in the room. And thanks, Gordon, for letting us drag it a little.